document, for example. And beginning this coming all faculty members are able to hear. Chakravarti garu already knows this. After the first few classes, mana classes lo there will be interactive exercises that we ask the students to do in groups. And then while they are doing it, the internal faculty members are mentoring them, guiding them to solve the problems. So we'll probably be starting that very soon, as early as next week. Usually the rule of thumb is 2/3 lecture, 1/3 problem solving in the classroom. Problem solving could be algorithms, it could be some practical real life scenarios like that. But what we can do is, to your point, Andy, we can do a similar internal mentoring session. You tell me when you want to do it, I am all for it. That's a great idea.
Sir, can
You got cut off there. Can you repeat?
Either on Monday, sir, Monday 9 to 10 or Wednesday 9 to 10.
Monday 9 to 10 అంటే నాకు సండే నైట్ అవుతుంది కదా ఇక్కడ.
Yes, sir.
Sunday night. I'm just coming back from Southern California. Sunday night అంటే మన క్లాస్ ఉంది కదా మండే మీకు అక్కడ.
So Monday we have class from 10:50 to 12:30, sir. So we can have this kind of interaction before that from 9:30 to 10:30, something like that.
I think that would be excellent. Let's do that.
Yes.
Monday, what was the other option that you gave?
Wednesday we have, sir. Wednesday from 9:30 to 10:30 or 10:30 to 12:30 or 11:30.
Let us take Wednesday.
Yes, sir.
Let's take Wednesday because I'm returning from Southern California, bringing my daughter back. Sunday by time my ఇంటికి వచ్చేటప్పటికి 8 or 9 అవుతుంది. And then Monday morning I have to go and set up my son. He's joining Uber on Monday. So I have to go and take care of him. So let's do Tuesday. Tuesday my time, that will be Wednesday your time.
Yes, sir. 9:30 to 10:30.
Okay. Can you send me an email? Then I can send a WebEx.
Yes, sir. Yes, sir. I'll send
Actually,
you.
నేను ఇప్పుడే పంపిస్తాను WebEx మీకు మర్చిపోకుండా.
Okay. So this is mainly for mentors.
Correct. Let's do that. So that is Wednesday your time, right?
Yes, sir. That is in India. That is 13th of this month, 9:30 to 10:30.
What we can call it is data structures.
Data structures roadmap for mentors. Internal.
I'm calling WebEx. నేను ఇది మీకు పంపిస్తే మీరు అందరికి పంపిస్తారా?
Yes.
Okay, one second. I'm actually doing it right now. One second, Andy. Okay, sent. You should have it in the next 20 seconds.
Yes.
Done. Okay.
Sir, I got the mail.
There you go. That's it. That's very good. Okay. Now any
On the internal faculty members.
Yeah. And then you are going to send me something about when your first midterm exam is going to be, right?
Everything will send.
Okay. Because that's how we can plan our pace of the course accordingly.
So I'll send
But,
the academic calendar. Like
I
list
think
of
academic calendar with the midterm and all that would be helpful.
Yes.
And then, as I said, beginning next week, they'll probably be doing more just like how you know my previous classes. We always make them do problem solving, kada. So they'll begin to do that. So good. So students, good morning everyone. And any questions? Join the Lensu thing. I have not checked yet. I should check how many people join. Give me a second. I'll check that. I can tell you in a minute. While I'm doing that, if you have any questions, just post them in the chat. I can answer them. Give me 1 second. Okay, if I say email members, wow, that is very impressive. Okay, I'm impressed. That is very good. So 175, I'm going to mute all of you now. Okay, I have muted. I know I'm assuming all of you are able to hear me well. If somebody has any problems hearing, please put it in chat and Chakravarti Garu will solve the problems. Okay, 175 people joined the community, which is quite good. So let me start off with a quote as we do that. Since Chakravarti Garu didn't put any quote today, I'm going to put one here now. Okay, so let me write it down here. That's easy, right? Wow. Why my whiteboard is not working? You see that? Am I connected? Can you guys hear me? Chakravarti Garu, can you hear me?
Yes, sir. Yes, sir.
Okay, excellent. You see that my whiteboard, which I'm trying to type, is not working. So let me open up this one here and type it there. I'm going to share my screen. Hold on. Give me 1 second, please. I'm typing some. Okay. After I type, I like this quote a lot. ఇంకా షేర్ చేసుకోవట్లేదు నేను టైప్ చేసి Okay, now I'm ready to share. Wow, something is not quite right with my. Okay, perfect. Let me make it slightly bigger and share it with you. Okay, ready to share. You know, my WebEx is not letting me share anything. Something is not right. I'm trying to share with you something here. Okay, I have to log back in. For some reason, it is not letting me share my slide deck nor my whiteboard. Why is that so? Okay, let me log back in. Give me a second, folks. I'm back again. Let me see if it'll allow me to share. Somehow my sharing is not working today. Um, wow, that is. I'm just thinking here. Give me a second. I'm trying to solve a problem here. You can't see anything that I'm trying to share, right? Why my sharing is not working? Mute all, invite. Okay. Okay. I'm so sorry. My sharing is not working. Chakravarti Garu, bear with me. I'm actually going to do a hard reboot of my system and then see if the sharing would work. Okay. In the meantime, just open up the slide deck there if you have it. And I can give me just 1 minute. I'll hard reboot my system and see if it works. For some reason, it is not working. Nope, it's not working. So I'll log back in. Bear with me. My whiteboard is not working. My sharing is not working. Nothing is working in WebEx. But can you hear me? Let, let me see.
Sir, we can hear you.
Yeah. So I'm trying to show you something. But today my WebEx I'm not able to share anything. Why I'm not able to share anything? The WebEx part, it is not letting me share. Neither is the whiteboard of the WebEx is working today. Can you take control, Chakravarti garu, and see if you can share anything from your desktop for a second? Let me pass the control to you. Do you take control? I'll say anyone can share. Can you take control and see if you can share
Sir,
your screen?
so yes, I can share.
Okay. So you are able to share. It's not working only on my end. So
Maybe
something happened.
some bandwidth problems.
Huh? No, it's not bandwidth only because I'm able to share my video also. Let me see what happens if I. Okay, now I'm able to grab the screen away from you and share.
Yes.
Okay, there's some hiccup happened somewhere. So let me then take the ball away from you and see, and then see if it works now. Hold on. Do you want to become presenter? Yes, I want to. Okay, let me see if it allows me to share or not. Okay, now it is allowing me to share. Excellent. Finally, that was a live demo to all the students. There was some bug which was preventing me from sharing. Chakravarti garu to control, and then now it is letting me share. Now, I just need to open my presentation and then we will roll. Data structures, unit 1. Yes, I am thrilled now. Share application, Microsoft PowerPoint. Excellent. Okay, now I'm sharing. Can you see it? Chakravarti garu, can you see it, Andy?
Yes, sir. Yes, sir.
Excellent. Guys, welcome to our class today, and happy Eid, belated Eid and all that. I hope you all had great festival, and you all went and saw the Eid movie of Salman Khan, Sultan. I'm yet to see that. We start off with a nice quote here. We are what we repeatedly do. Excellence then is not an act, but a habit. Very famous quote of Aristotle, one of my favorite philosophers. So keep that in mind. Nobody becomes excellent just like that, right? So you have to make it a habit. Chala mandi we often say, "Oh, this guy is brilliant. He doesn't work hard." Believe me, behind every brilliant person, there's a lot of hard work that goes into play. Okay, um, I wanted to ask a question. Just to remember, I said we'll ask a lot of questions in this class, right? Let me start a new slide here. Let me call it a new slide. Where is the new slide? Why my? I hope somebody didn't hack into my machine today. Okay. Small problem. I'm actually cheating. I'm taking this small problem out of a book. I'm going to talk about a problem, which book in a shortly. So let's say you have a string. Okay. Let me take this off. So funny, it is not letting me. Let's say you have a string, okay? Everyone knows what a string is, right? If I say this is data structures class, okay, that is a string in double quotes. Please mute yourself, folks. Let, let me mute all of you. Somebody has, let me mute all of you. Okay, I muted all. So let's say you have a string. This is a data structures class, right? So what could be a good algorithm to determine, or let's say you are asked to determine, I'll put it in a different way. You're asked to write an algorithm, okay, to determine if the string has all unique characters. Okay, let me put it in a presentation mode here. Let's just have some fun instead of just listening to a lecture. Let's see if we can spend some time here. We are actually starting off the class. You're getting a sample of the problem that we try to solve here, right? So I'm asking, you are given a string and your goal is to write an algorithm to determine if this string, not the string, if the string has all unique characters. How would you do that? What is that algorithm? Anybody wants to? We'll do it as a group, okay? Next week onwards, I'll assign specific time and you will do it in groups and all that. Small groups where I'll give you 15 minutes. But here the group is one big class. So who wants to start first? How would we do that? Some ideas. I want some ideas. Give me some ideas. So what is the way we can go about starting it? Anything goes, okay? This is a brainstorming. By the way, even I don't have a solution off the cuff, okay? We are only brainstorming here. If anybody wants to talk, they can unmute or they can put it in chat. I'll monitor the chat. Back screen learner. Okay. So here is the problem. There's a string that is given. If the string has all unique characters. Unique ante, I mean, a character is not repeated. Okay. For example, in that string that I gave you, S is not unique. S is repeated multiple times. T is not unique. Repeated multiple times. Who wants to? Okay. Somebody said by using ASCII values. Okay. Um, that does not. That's not an algorithm, but it's a good one. I mean, ultimately, I think you map it to an ASCII value. I agree. Any other ideas? I should see the video of students. Okay. Jntuk Kakinada said ASCII values. So what do? You read each character. Okay, let's say I read the character. When I start reading the string, in your C programming, you would have written some programs, right? To read a string and print it out. I'm assuming you wrote some programs like that. Because any programming class, there'll be some string manipulation. Okay. So what do? Like you say, while not end of line ಅಂತಾರ slash n కదా, all C strings terminate with a slash n. You read the character. Okay, so I read T, first line, I read T. So is that unique or not? How would I know? I would not know anything to begin with because that's the very first letter, right? So Jntuk Kakinada, what you wrote there would not give the full meaning. So if you want to expand on what you said, they are making you think right off the bat. Faculty members also are welcome to help here. We are trying to do some kind of a group think tank here. By the way, where would you store this string? How would you store this string in C programming language? So, uh, what kind of variable do you declare in C programming language to store a string like this? Who can answer that? Which student can answer that? Anybody? I see pictures of Jntuk Kakinada. I see DMS, SVHC, character. Excellent. Private పెట్టక్కర్లేదండి. Whoever character array, right? You can actually do a char star and then declare a string. Okay. So once it's an array, then what can we do? Remember we talked about arrays, correct? So you have array, all of these things. So if I have to put it in order for me to type, I cannot put it in a presentation mode, as you know. So I have to do it like this, right? So if I go here, if I have to draw an array table, let's say I just do something like this, a small table. Okay. And then I say this is right. This, I'm typing something here. Give me a second, I'll expand it. This is, okay, something like this I do. Okay, that is my array. Okay, what do I do next? So you're basically writing an algorithm right now using a data structure that we learned. Let's make some more progress beyond simply saying, okay, we have an array, we save it there. Char star, we declare an array, and then, all strings are terminated with backslash n. Let's assume all that is in place. So then what is the next thing that you do in your C programming? Do you use some kind of a while loop? Okay. So somebody said, again, privately, don't put in privately, put it to everyone. Somebody said here, I'll put it for the benefit of everyone. Compare each character with remaining character to find duplicate. So I have T, then I say read the next one, right? That means I say array some variable. Let me write it here, okay? Uh, Again, I have to take it away from presentation mode to make it small, right? Give me a second. See okay, now I am in presentation. Okay, okay. We'll spend some time on this, okay? That way we can all think through and see how an algorithm can be developed, right? Okay. So that's true. You are using, okay, that's good. I increased the volume, I increased the font size so that way you can see it too. Actually, I zoomed. So somebody said that we can do if I do a text box here. So you're saying you can say get So you say read first character. Okay. So when you read first character, let's assume you read that first character into some variable, right? I'll say variable is ch. So you are going to read the first character. Okay. So ch would have t. Then what do you do? Compare ch with, and then I is the array index, right? You have to put the array index, right? Array index is I equal to 0. Okay. So this is read A0 instead of saying read. Let's call the character array as A. I'll say something like this, correct? Okay, so A0 and then CH has T. Compare compare CH with A1. That's what the algorithm is. Okay, if I compare, yes, they are different. Does it give anything? Does it give anything in terms of a solution though? So yes, T is different, H is different. They are not same. Then what do? You compare the next one, right? Because so far T is unique because second letter is not that. So you can actually then, this is a very, it's a simple algorithm, right? So you compare CH with A1, then you do the same thing with A2. I think that's where you're heading, right? And so on until end of the string, right? Okay. So if none of the comparisons work, meaning they are not equal, then that A1 is or A0 is unique. Correct? You agree? Yes, no, perhaps. So you read the first character and then till you reach end of the string, you're comparing every character to the first character. If none of those things match, the first character is unique. Okay. What is the algorithm? How does it say how many? Did it say how many unique characters are there? That's what I think we said, right? In the problem statement, we said if the string has all unique characters, right? So then you bound it with then what do? You increment you increment the counter to A1. A1. Okay, then what do? Then do you compare A1 with again A0, A2 and so on? Or you don't need to compare A1 with A0 because that A0 and A1 have already been compared. How do you program that? If you don't have to answer it if you don't know it, but I'm just making you think. So in essence, when you have, let us say, if I were to put the alphabet there A to Z in an array, and if you are using this algorithm to see if all of them have unique characters, obviously all of them have unique characters because I wrote from A to Z, right? But every single time you are incrementing it. So how many times you are executing that loop? In essence, there's a loop here, right? For 26 characters, you are essentially comparing it 26 times like that, right? 26 times you are executing the loop. Am I am I am I making sense to you? Right? I can see based on the algorithm that SVECW gave here. Did SVECW or who gave it? Somebody gave the algorithm here. So PSCMR. So you are basically comparing every character with rest of the characters. So if I have a 26 element array, I'm doing that loop 26 times. 26 times 26 actually. 26 letters times 26. That is the number of instructions that I have to execute to determine about the unique characters, right? Okay. Now, we don't have to take it further because I want to cover some of the material. Uh, think about it. I'll post this question in the community. Uh, you can figure out, because you have learned the concept of arrays. You already know the concept of programming, and I'm asking you to write an algorithm to find the unique characters, and you can do some variations of it. Okay, I not only want you to find the unique characters, how many of those unique characters are there? Okay, if there are two unique characters, you should say 2, 3. So you're just adding to that problem to figure out a solution. And let's see who can come up with the quote unquote. Remember, if you all come up with different algorithms, you have to figure out which one of them is the most efficient, right? So what are the two things that we talk about in terms of efficiency or complexity, as you want to call it? One is the time complexity that we talked about, how much time an algorithm takes. And the other one is storage complexity, how much storage something would take. Ignoring storage for a second now, let's worry about only the time complexity for this particular problem that I posed. Okay, so now let me show you. Am I sharing my video or I'm not sharing my video? Let me check. Looks like I'm sharing my video, right? Check it out. Are you seeing my video on it? Because I'm having some difficulty here to
Sir,
raise.
I can see your presentation and your video.
You can see that. Okay, thank you. Great. Because I'm trying to move my screen and then it is hanging. And now it is moving. There's some small problem here. I'm going to show something. Let me know if you see this. Do you see this? If you see it, can you read it out?
Creating the code review, interview.
Okay.
Sorry, cracking the
So
code review.
yeah, cracking the code interview.
Code interview.
Okay. I'll put it in the chat here for everyone. Okay. Cracking
Sir,
the coding interview. Cracking the coding interview. Okay.
sir, if
Put
any
it in the
colleagues they
chat.
have bandwidth problem, they cannot see your video.
They have bandwidth problem. They cannot see my face, but they can see what I'm typing in the chat, right?
Yeah, that they can see.
Yeah, exactly. That's important. So I put the textbook title there, Cracking the Coding Interview. This is the most, I would call this your Bible to get a good job. Okay. If all faculty members, in case you have not seen this book there, please make a note of it. Every computer science student should have this book, because it's basically cracking the coding interview, because you can get a job in the Google and the Facebooks of the world. Okay, and what does this book cover really? It has about 150 programming questions and solutions. And all the programming questions and solutions revolve around data structures, strings, arrays, trees, hash tables, okay? And questions such as the one that I gave you right now as a sample. Okay, so every student who wants to really learn programming and data structures should know in and out of that book. That is how, for example, my boys got great jobs in companies like Uber and their other good friends. Huh? Oh, name of the author. Somebody asked name of the author. Uh, I can put it here. Gaylakmann, dowel. So even my son was telling me that, Papa, every Berkeley student, all of us, we know pretty much in and out of this book. That's how we get jobs in Googles and Facebooks and Uber, Microsoft, LinkedIn. Pretty much you name any top 50 tech company in the world, they ask you questions from this book and they all go prepared. Okay. So I'm sharing some secrets with the students here, which would make faculty members like you all and me useless compared to them. Okay. But it's okay. The students will benefit. So we will be actually tackling some of those things as we go along here. So I will talk more about those things, Chakravarti garu, when we do that faculty mentoring session next Tuesday. Okay. Okay. So let's continue with the lecture. I put a uh, big slide deck there, and we stopped in the middle, right? So I don't remember where I stopped. Anyone has any idea where we stopped? I think I know where we stopped, but um, let me, yeah, give me a second. Hmm? I think we stopped. We covered. I think I'll start here, and then I'll breeze through it if we covered it. Did we cover this slide last time? Yes or no? We said an array is nothing but contiguous locations, right? I recall telling you that. This is how we declare arrays. I recall telling you this too. Okay. We said how you declare an array. I gave you some examples. Thank you, Pragati, for letting me know. And we said we can initialize the arrays. Okay. We covered this too. Remember, I think this is where we stopped last time, I think, right? We said there's a famous algorithm called bubble sort. And then I think we covered this and I gave you some high level description. And I asked you to go do some Google search on bubble sort and understand the algorithm well. Okay. Thank you, Raju, saying that we covered. Okay. Then we said we will, that is one thing. That is the sorting part. Entire computer science literature on this can be covered in sorting and searching, right? So we said searching, we can do multiple ways of searching. We said an array, if you have an array, we can search for a particular key value, and linear search is nothing but going sequentially. Okay, compare each element of array with key value. Isn't that what we have done in the problem that we started off the class with today? Remember how one of the groups here said, hey, compare the element with every other element in the array. Okay, so in essence, we are kind of doing that, right? But we said that if you're doing a simple search like that, it is useful for small and unsorted arrays. Okay, but if you have a sorted array, it makes it slightly easier if you're searching for something because you can always compare the key with the middle element, and whether the key is less than the middle element or key is greater than the middle element or key equal to middle, we can cover the searching fast. If key is the same as middle, then we found the match. If key is less than middle, you eliminate the right half and then look only in the first half of the array. Okay. Then we said when we talk about analysis of algorithms, we have an algorithm, we are talking about an input to the algorithm and an output. Okay. So we take the inputs and we convert, do some activity or actions on that, and then we go to the output. Okay. Now we said that as the input size grows, the running time grows. Obviously, to process to process 100 records takes less time than to process a million records. It could be the same algorithm, right? So obviously the running time grows with the input size. Okay. And then we said we typically try to focus on the worst running time, meaning what is the worst case? What is the worst that can happen? And I think I mentioned to you the concept of the big O notation there. We said, hey, we'll be covering the big O notation, which essentially focuses on calculating the verse times. Okay. Another way of doing it, instead of theoretically analyzing, the other way of doing it is we can do experiments, right? That means we keep running. Okay. We run it with the inputs of varying size, and then we get some kind of a graph of the results. That's another way of doing it. But most often running experiments is an expensive proposition, so we use a lot of great mathematical concepts like the big O notation and theta and omega to understand the efficiency of the algorithms. Okay, that's the reason why we said that experiments are very limited, because we have to implement the algorithm in a computing environment. First of all, that itself could be difficult. Okay, and then all said and done, just because you get some running time, it still does not give you formally what the complexity is. Okay, so, and then the other one is to compare two algorithms. The same hardware and software environments must be used. By the way, this is a good exam question for you. Knowing India, and since I grew up in India, I know these are the type of questions that are asked, or they used to be asked when I used to take exams there. They would say, hey, list down at least three reasons why experiments have limited capability when it comes to understanding the time efficiency of an algorithm. So these are some bullet points for you to understand those things. Okay. So as I said, we use the theoretical analysis, which would allow us to compare algorithms in a more systematic and formal way. Okay. I don't know, we talked about this or not, but stop me when you see something new there. We said that when we are writing an algorithm, we are writing it in pseudocode format. And what is pseudocode? Definition, right? Again, good to know the definition, even though I would not ask such definitions in my exams.
చెప్తున్న వాడిని
Is
రాసుకోండి. ఆల్మోస్ట్ ఇవన్నీ మనం క్లాస్లో విన్నవే, కాకపోతే పాయింట్స్ అనేవి మనకి దొరకవు. క్లియర్? స్లైడ్స్ అనేవి ప్రత్యేకంగా తయారు చేసి
got it. మీరు ఎవరో చెప్తున్నారు రాసుకోండి any points. That's good అండి. Thank you for that suggestion. But all slides would be in the community. Um, for some of you, if by writing you will understand it better, by all means. But those of you who cannot write fast, that's okay. No worries. Okay. Everything would be there for you in terms of notes and slides. Did we write pseudocode in the beginning of the class today? Absolutely, yes. That was pseudocode, right? We wrote some high-level descriptions, but in the process of high-level descriptions, since we are computer scientists, we combine we combine English with some programming language concepts. For example, I put a variable C there, CH, right? That is a computer syntax, right? So you combine your English some high-level programming syntax, and we said, hey, repeat the same thing throughout the array. Repeat is nothing but we use something like a while statement, right? So these are all pseudocode stuff. Okay. Definitely less detailed than a program, because I did not mention anything there about whether it's an integer, array, character. Remember, in C language, you can declare an integer array, but you can store characters in an integer array, right? So we didn't show all the types and all that. That's why it is less detailed than a program. Okay. And of course, it hides the program design issues, because we are only trying to do it at a high level. We are not taking into account any architectural or design issues. It's all there. Okay. So here are some examples. I don't think we covered this last class, but I'll go slow now. So you can see here, to show control flow, we use if then else, while some condition is met, do something. These things should not be new to you, because you have done C programming. In case you bunk classes like how I used to, then maybe this is another opportunity for you to learn these things more systematically. Okay. For the purpose of this class, I'm not really making any assumptions about your competence in the C programming language. It would be good if you're competent. If you're not, if you're sincere, you can still learn it here as part of this class. Because we always recommend writing some programs, right? A data structures class without writing programming is in my opinion totally useless. Okay. Okay. ఇక్కడ మనము we started covering some, either we covered or we are doing it. Basically, when you are talking about analysis of algorithms, these are the type of thing that we come up with. We say, hey, whether the function executes in constant time. If you take, for example, what is an example of that constant time? Constant time is any computer to access any RAM location is a constant time. Whether you access memory location 1 or memory location 64 gigabyte location, it is the system always executes that in a constant time of 1. Okay, that's what is constant. Then of course you have linear, right? Linear, everyone knows linear, right? And then you have some algorithms which would take n log n. Okay, quadratic, meaning it's of the order of n squared. If you have two for loops, if you remember, for example, say matrix multiplication. Okay, if you have to multiply two matrices, if you have written your C programming, you would know that there are 3 for loops, right? In a matrix multiplication. చక్రవర్తి గారు కరెక్ట్గానే చెప్పాను కదా నేను అది matrix multiplication 3 for loops. Other faculty members can help me out too. If I remember right, it has 3 for loops. Okay. If you multiply an m by n and an n by p matrix, okay. So you will see that when we do the algorithmic analysis, we say, hey, there are 3, it's of the order of n cube. Thank you, PSCMR. By the way, if I don't know something, I never feel shy of asking even students to hear. So it's not like I'm an expert in everything on earth. None of us are, right? So please help me out whenever I'm screwing up something here. Students can help me out too. N log n, quadratic, cubic, exponential. Okay. Now, the ideal thing, I mean, nothing, you very rarely find algorithms which are constant. Okay. The goal is, I'll put it in chat also. The goal is if I can get a log base 2 okay. So log base 2 n low. If you take binary search, okay, binary search is a log base 2 n algorithm. If you have to search 100 elements, it's very easy, right? To I want you to think about it for a second here instead of getting lost, right? Let's say I have a 100 element array. Okay, let me write it here, okay, to bring out that point here more clearly. Okay, that way you don't feel rushed. uh, if I were to do a new slide here, new slide, okay, let me say layout is just one. Okay, I zoomed it enough so that way you can see. Let's say you have 100 element array. You are able to see what I'm writing, right? Okay. So if I'm looking for and let's say I'm looking for some key value. Key value. Okay. How many times I have to search the array? Can a student answer that question? Potentially. Worst case. Remember, algorithms usually were best case. You can tell me best case and worst case also, no problem. How many times I have to search the array? Best case low. Let the student answer that, faculty members. I have a 100 element array. I'm looking for a key value. What is the best case? Okay, I'm assuming it's the student who answered that. Pragati 1, exactly. Worst case, again, I'm assuming it's the students who are answering that, not the faculty members. Okay. If that is not true, if faculty member is answering, that's fine. They can let us know. Worst case. Okay. Now the same, this is linear search, right? Let's take the same element array, but except it is sorted, obviously, binary search key. Let me cut this off. It's amazing why my system, my laptop is not behaving correctly. I'm trying to delete that. Okay, there. Okay, now assume it is sorted and you're finding a key in this array using binary search. What is the best case? Okay, Pragati said 99 worst case. Yeah. Understood. 99 or 100, I'll give you the boundary error there. I'll give you the benefit of the doubt. Okay, what is the best case here for sorted array here using binary search? 1. Perfect. I'm so happy. There are different institutions they are typing there, not just one institute. Chakravarti gar knows who I'm referring to. Okay. Best case is 1. Okay. Now, what is the worst case? Huh? Somebody said 50? Somebody said 50. Okay. Uh, there you go. Mhm. Again, PSCMR garu. Never don't need to put it in private. Always put it for everyone. Unless I say put it in private. Okay. Log n. Somebody said 6 5. 10 unne kada. 100 undi. 100 lo we're talking about. So from 100 it goes to, after first search it goes to 50. After the second search it goes to 25. Remember, we are cutting it in half. So 12.5 ante, I think it always rounds off to the next higher number, I think, in binary search. 13. 6.5 ante 7. 3.5 ante 4. Then 2. Then we are done, right? 2 తర్వాత మళ్ళీ 1 చేయాలా? 1 అంటే ఆటోమేటిక్లీ వచ్చేస్తుంది కదా. Okay. So basically 1, 2, 3, 4, 5, 6, 7. So I'll give the benefit of the doubt. I'll say it's either 6 or 7. I don't know what happens. When you come to two elements, uh, thank you. That was my dogs barking and my son came and closed the door for me. So, um, so when you're left with two elements, you compare at least once, kada? So then can one and also. So 1, 2, 3, 4, 5, 6, 7. In essence, it's logarithmic, right? Basically, as somebody said. Okay, Usha Rama College 90 is not, somebody said 90. Probably you meant 9. Right? That's great, but I got a lot of answers, 6, 8. But you get the idea, right? Compared to a linear algorithm, binary log 2 base n is always much faster. Okay, that is all students. I don't know how many students are there. All of you combined are probably 400-500 students or 300, whoever, right? I want each one of those students to understand this concept. This is what makes a good programmer stand out compared to a not so great programmer, right? So always aim for log 2. If we can do better than that, there are better algorithms than that too, but that gets into deep research areas. We'll not go there. Okay, fantastic. Okay, are you guys having fun? Okay, so this shows some graphs here. This is standard high school arithmetic, right? You learn about these things in graph when you're graphing algorithms and things like that in your calculator. Okay, I'll not spend time on that. Now let me put it in slide mode here. Okay. 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 So what we do when we do these things, right? Initially we start off, one way of doing is to count what are the primitive operations in a given algorithm. Okay. So we can identify those things. Okay. And most of these primitives, they are largely independent from the programming language. We assume all things are equal. Okay. Programming language, um, hardware environment, software environment, right? We need to have some constant framework in order to evaluate things. That's called the reference framework, right? Okay. If you assume all of these things, okay, we'll figure out what the primitive operations are. Okay. And then we also see that last one, two, three, four, fifth bullet point here. We assume to take constant amount of time in the RAM model. Okay. So here are some example things: evaluating an expression, assigning a value to a variable. Like if I say A gets 5, that's a primitive operation. A primitive operation from the viewpoint of a high level programming language. Okay. A simple operation such as A gets 5, if I have to show you how that happens in the register level in a HP's precision architecture chip, it could take 4 steps. Whereas in a sun environment, it could take 3 steps. We are not going that low level here. We are still keeping it at a high level. Okay. So we compare the number of primitive operations that are performed in different algorithms, and the one which performs the less number of primitive operations is a better algorithm, rule of thumb, right? Okay. So how do we count the primitive operations, right? So let us look at this example. I think if I remember right, I think we kind of showed this and we stopped. So if you look at this example here, step 3, I'm just reading out from the slide here. In step 3, you see integer n equal to data dot length. Okay. So it has 2 operations. What are the 2 operations there? You can put it in chat. It might be a trivial question, but I would still like you to go ahead and answer that. Obviously, you're looking at some Java code here. You probably would not have taken a Java class. You only took C programming class. Okay. Okay. Somebody put the answer there. Let's do that. Length and assignment. Thank you. Length and assignment, right? Change CNG for a meeting with a. Okay. We are okay. Thank you. Thank you, Chakravarti Garu, for letting me know. Okay. Um, See, I'm so excited. I didn't even take my coffee break today, but that's okay. So two primitive operations, as somebody pointed out from DMS. One operation is data.length. Data is nothing but it's an object. When you take my Java class or somebody else teaches Java for you, you'll see that this data is a data.length. The left part of the dot is called the object, and length is called the function or the method. Is the method of that object. Okay. So by that is one operation. You're telling the data object, hey, what is your length? That is one operation. The second operation here is the assignment. So that is step number 4. You will see 2 operations because data 0, you're accessing the array element. That's one operation. The second operation, the assignment. Okay. So um, step number 6 is 2n ops. So how do you get the 2n ops there? N ante some value of n, right? Akkada j, you have a for loop there, right? So you're assigning j some initial value. You're doing the for loop basically n number of times. Now 6th step has about two operations. So that's why it is 2 times n ops, because you're doing the loop n times. Like that, you count the number of operations. Okay. So in this case, if I ask you, hey, how much time it takes, what is the time efficiency in terms of the number of primitive ops, you should be able to answer that question easily. You got it? Give me a second, please. I accidentally turned off my light here. Okay, got it. Okay, let me pause here. Any questions, comments? I asked a question, are you guys having fun? Nobody answered. Maybe you're too engrossed or you're already sleeping there and I can't see your video. Okay. The more fun you have, the more fun I will have in the class. I can tell you that. Okay, I'm seeing DMS SV. Show of hands here for a change of pace. Are you having fun? How many of you would raise hands? I'm looking at the video of DMS SVHC. ఎవరు చేయలేపట్లేదు ఒకళ్ళేదో మొహమాటానికి లేపారు ఓకే 2 3 4 that's it. Other half is not having fun, then you should not be in the class. You should go out and watch a movie. Yeah, now all of you are raising hand. That's excellent. Yeah, we are supposed to have fun in my classes. Okay. Okay. JNTU faculty వీళ్ళందరూ ఏంటంటే నన్ను కొంచెం సీరియస్ చేశారు. I must admit that. See, I am the guy where I go teach my classes with a cup of tea in my hand throughout my lecture. And one faculty member gently told me in one of the classes, even they are not allowed to bring tea into the classroom. It kind of took away my free spirit. Okay. Estimating running time. Now imagine if you have to count the primitive operations like that, right? Um, It'll give you some analysis here. I won't go through every sentence of every slide. But if you have, let's say it executes that array max that he gave, it has 5n plus 5 primitive operations. Okay. And then worst case 4n plus 5 is the best case. Okay. Which is fine. Let's assume that the equation that he came up with by counting is correct. Okay. Now, when you have 5n plus 5, as engineering students, what would you approximate it to? If I have 5n plus 5, what would you approximate that number to? Basically, if you have worst case and best case there, the value is going to fall between those two. But if you are doing some quick and dirty analysis, when you have a 5n plus 5, is approximately what would we approximate it to? Do we approximate it to 5? Or do we approximate to 5n? Okay, 5n, no brainer. Excellent, thank you. Okay, now when you have 5n, do you approximate it to n? Is it approximate to n? So from 5n plus 5, we made it 5n. Good. Now, do you further approximate it to just n, or do you keep 5n? We all learned a lot of, typically in math we learn these approximations, right? Somewhere. I don't know where they teach, high school or first year college, wherever, right? So as n increases, the value, remember as n approaches infinity, the value 5, does it really count? We remove 5 also, right? We simply say it's n, right? Typically. As n becomes larger and larger, where it is 5 times 1 million or 1 million, it's still a large number. So we remove 5 and we approximate to n. So that is the reason why if you see the Tn here we're talking about in our algorithm analysis, we are always looking at that n. That is why somewhere here, Ecuador, one of the places where it will come, we call it asymptotic analysis or asymptotic algorithms because we are basically approximating it. We have an upper bound and our algorithm approaches curves. When I show you some curves, it will be less than that so-called upper bound with all the variables. Okay, keep that in mind. You can see that here, right? So he is comparing two algorithms here. Now you don't know what these two algorithms are. One is called the insertion sort. The other one is called the merge sort. Okay. You do not know how those algorithms look like. We'll have an opportunity to look at some of those things as we go along. But it so happens the insertion sort, it is of the order of n squared over 4, whereas merge sort is 2n log n. Okay. Now you can see the data here. It's pretty amazing. See that one here? If you're sorting a million items, insertion sort takes roughly 70 hours. Okay, whereas merge sort takes 40 seconds. Okay, the same thing if you're doing in a bigger machine. Remember, somebody asked me very first day of the class, machine conditions and all of those things, how would they impact? You can see an example of that here, right? If it's a faster machine, one is taking 40 minutes, the other one is taking 0.5 seconds. Again, which algorithm is better here? No brainer, right? The merge sort is a better algorithm than a insertion sort. See the power of algorithms there, right? That's what I want you to appreciate. Um, there's so much PhD research goes on in this still. You would be amazed. They save milliseconds too. Because over a huge, humongous amount of data today in today's world, in the e-commerce world, or if you look at the cloud computing, right? What is the storage that we have? Petabytes of storage. We no longer talk terabytes. We talk about petabytes, right? And then because you have big data, there's a lot of data and you have to process them. If your algorithm is not efficient, then basically people who are using your code can go watch a movie and come back and your algorithm is still running. Imagine 70 hours. I can take a nice trip to Europe and come back, in 70 hours. Okay, so that's why it is very important. Now, that is why you should all be reading the book. Everyone should have that book called Cracking the Coding Interview. Okay? Okay. So, what we do to compare these things, and since it is very hard to count the primitive operations and all for anything beyond one page of code or two pages of code, we have some mathematical analysis. And the biggest one, the most famous one that we use is called the big O notation. Big O is nothing but a big capital O, okay? So with that, we try to understand the limiting behavior of function, okay? As the arguments tend towards some infinity, right? What is the how much time an algorithm would take were in the worst case, okay? I have some very nice notes on that, which I'll put in the community as we go along, okay? Okay. So here is some example that the author has given, okay? So like if a while loop is executed n times, right? Uh, if you have 3n, you still approximate to n, right? And you can see how, I think he's showing the array there, right? You have an array L of n entries. We did the same thing, right? Even before we came here, we did the array index, and here he's doing it as a linear sequential search. That's what we call linear search. And then he gave the full code as to how to search for it. And then he calculated all of those things. And then he said, okay, when I calculate the primitive operations and all that, I have the highest degree term in n. Since the highest degree term is in n, I will eliminate all the other constants in that equation and then use the of the order of n. We don't say this algorithm is the order of 3n. We always say it's an algorithm of the order of n, because as n tends to infinity, 3n also is infinity. Okay? So you can see here um, different it's like a formal definition here. Um, Even if you don't quite understand the formal definition, it is okay for now. Okay, later on I'll give you much simpler definitions. Okay, so what we are doing here is we are showing how a big O notation is basically being compared to um, what is the right way to say it? Let me think. Okay, big O notation is a limiting factor, right? So that G, to show that approximation, you have to take two functions. One is f and one is g. Okay, to begin with. That's why let f and g be functions on the set of integers. Okay. Okay. Then we say the function f. Okay, is said to be of the order of gx. Okay. That means fx is the big O of gx. Okay. That's why you see fx is big O notation here, gx. Okay, provided the conditions are met like this. What are the conditions? You have some constant c and no such that this two vertical bars, right? That is the magnitude. The magnitude of fx is less than or equal to c magnitude gx whenever x is greater than no. Okay, some value of x which is greater than some constant no. So when you do this limiting fractions here, this simple math, guys, by the way. Okay. So if you see the g function going up like this, whereas f is always after a certain point, in this case it is 10. Okay, f tends to be lower than g because you're eliminating the constant factors there. Okay, so if you look at the values that he has given in the table, uh, the break-even point for Fn and Gn for that equation that he has given above, 100n squared and Gn equal to n4, when the value of n equal to 10, those two Fn and Gn are same. You agree? Right? You substitute n equal to 10, the values are same. But the moment you go past 10, in this case you're showing 50, Fn is 250,000, whereas Gn is 6,250,000. Okay. Now what happened here all of a sudden? At that point, GN is rising asymptotic larger and larger, right? Compared to FN, because it's order of the 4 there. So by removing this value 100 also, right? This n squared can never reach that n raised to 4 value there. Got it? So that constant is not making any difference in the analysis. That is the reason why we say, hey, we remove those constants, but to define it mathematically, we needed that equation here. Magnitude of fx less than or equal to c magnitude of gx whenever x is greater than n0. Why we said x is greater than n0? In this case, from the above equation, you can see that n0 happens to be 10 in the above table. Okay, when the value goes beyond that, fx is going to be less than or equal to cgx. Okay. Okay. Again, for now in your mind, you can just say it's we are basically taking the this is where the practicality comes into play, right? Nobody in the interview is going to ask you to write that equation like that. They will say, hey, explain what big O notation is. You say, yes, big O notation is always dealing with the worst case analysis. That's it. That is point number one. Point number two is the way the big O notation works is uh, it considers the variable n. As n increases, what is the result? Okay, because as n tends to infinity, all the other constants are meaningless. So it removes all the constants and all of those things and focuses only on the variable n. Okay, that is why it is called the that's why it's called the asymptotic behavior, because if you consider all the constants and all that, that is the absolute thing. The gn is the absolute one. Okay, so by removing those things, we approximate it, and that is the big O notation. Okay, now when I post my Word document about the cheat sheet, you will see some nice definitions as well as a lot of examples. Okay, here is one example like that. I think I may have this example too. So when I give you an example 2n plus 10, I say, tell me what is the order of. You simply write as order of n. Okay. Now, how did you get to order of n here? I don't know if in your exam they'll give you some problems. Okay. They can give you a thing there and say, okay, tell me what is the value of c and what is no here. They might ask you that. So you then do exactly what it is done here, right? What is the equation? 2n plus 10 is less than cn. Going back to fn is less than or equal to cgn, right? Remember this particular formula here. Fn less than or equal to cgn. One second. Okay. So 2n plus 10 less than or equal to cn. And then you do the simple math here. You figure out what n value should be, because after that point, fn is going to be less than the gn, remember? So n is greater than or equal to 10 over c minus 2. So we pick some values, c equal to 3 and n equal to 10. And those are the values. So when you plug in those values, beyond those values, fn would always be less than or equal to cgn. Until then, it will be on par with gn. Fn would be on par with gn. But beyond those values, fn would always be at the lower end compared to gn. Okay. Okay. One more example here. N squared is not of, or if I say n squared, right, it shows that it is not order of n. Okay, big difference. Say, oh, n is infinity, but n squared, why can't we put it as n, right? In order to do that, if you look at the based on the equation here, right, n squared is less than or equal to cn. That means n has to be less than or equal to c. Okay, the only way it can be done, you can satisfy that is c must be a constant. If it's not a constant, you cannot do that. That is the reason why when we say algorithms are of n squared, you cannot argue, hey, based on the approximation, can be call it of the order of n. You cannot do that because the inequality cannot be satisfied. Okay. Okay. Uh, Quick, rapid fire answers here. I should keep track of the time too. I still have 10 more minutes, right? Okay. So you can see here, first one, 7n minus 2, it's of order of what? Type it in place fast. 7n minus 2 is in big O notation, it's the order of what? N, right? I'll give the first one. Second one, 7n minus 2 is of order of n. Equation there, big O. N cube, thank you. Third one, log n, you got it. Okay, that is good. Now there's some formal analysis here, like the big O notation gives an upper bound on the growth rate of function, because it's like pretty much the worst case analysis, right? And then how we read this fn is of the order of gn means the growth rate of fn is no more than the growth rate of gn. Why is that so? Because in fn, we are eliminating all the lower order terms, whereas Gn has all of those things. So that is why Fn is always lower than Gn. Okay, and then we use the big O notation to what happened. I went somewhere here. Sorry. Okay, so um, small table here which shows that when Fn can be equal to Gn, right? So we'll look at some of those things when we get into omega and theta notations. You will see some real examples of that. Okay, this one next. Okay, some rules here. Hmm. So what we are saying is basically if you look at the first bullet, we are saying you drop the lower order terms. Second bullet was, what does it say? If you have 2n, you say order of n, because remember we remove the constant. Okay, instead of saying order of n squared. Okay, and then 3n plus 5, again removing the constants, you call it order of n. Instead of 3n plus 5 is order of 3n. Remember very first example that we did, when we had the 2n plus something, we removed the constant, then we removed the 2 also. That is what this is saying there. Okay, so there will be some practice problems for you to do on the big O notation for you to feel some comfort level. Okay, so that's why we call this asymptotic algorithmic analysis, right? Because we are always approximating it to our reference point is g of n, whereas f of n is always less than beyond a certain constant factor, right? Remember we took those two constants c and o, and beyond a certain break-even point, fn is always lower than the reference graph for gn. Okay. Now, how do we do this asymptotic analysis? Uh, we find the worst case. Okay, number of primitive operations executed as a function of the input size, and we show that in the big O notation. Okay. Now, when you go back and look at the slide on array max that we did, it was some 2n plus 5. So we eliminated 5, we eliminated 2, and we said it runs in order of n time. Okay, got it? Okay, so that is the reason when somebody gives you algorithms, the reason why they're able to come up uh, what the order of the algorithm is in a quick way is, first and foremost, intuitively you count the for loops. If you have the same problem that you're solving and one guy used 3 for loops and the other guy used 2 for loops, it's a no-brainer. The guy who used 2 for loops wins because if it's the order of only n squared. The guy who used 3 for loops, it's the order of n cube. Okay, so when I'm doing that, it had so many other statements too, right? Which had some additions, multiplications, whatever. But those are all constant. Wherever there's a variable like an n, that is what I focus on when I'm doing the analysis. Okay, you got that? Okay, I hope you got that. Now, for those of you who thought you you don't need to remember your math, the book very nicely says, this author Goodrich says very nicely, you better go review your math. Believe it or not, I am now at a stage where I don't remember my math. Even my daughter, who was finished 10th grade, when she was doing some pre-calc, just when was it? It was actually 3 days ago. She was doing some practice PSAT books, that is SAT. You probably heard of that, right? Some triangles it was given, and some equation they gave, and they have to figure out a solution. Uh, simple geometry slash algebra problem. Uh, I couldn't do it. And then my wife was, and I'm supposed to be a math whiz kid in the house. And then, of course, my wife promptly did it. And I had to go ask her, hey, how did you do it? I couldn't do it. It was so embarrassing to admit because they know that I'm a math wizard, right? She said, don't you remember the property of similar triangles? See, that's what old age does to you. I couldn't remember it. But you're still too young, so you review your math here. When you're doing algorithmic analysis, this maths would come in very handy. Okay, whatever is shown here. A raised to b plus c is ab, a raised to b, a raised to c. Most of you would remember that. But all of these things is what is used in analysis of algorithms. Okay. Okay. Let me check the time, and then I have a little bit more time, but I'll just introduce you to this slide and we'll cover it in the next class. Or let's see. Yeah, let me try to cover it here. I'll just introduce you to it and we'll go into details later. Okay. So in addition to big O is the worst case, right? Uh, you have two more notations called big omega and big theta. Okay. So here are the formal equations there. The omega notation, you can see how the Greek alphabets, right? So you have the worst case analysis, you have the best case, and then you have the equal to. Okay. So big omega and big theta basically covers all the things. Remember in math we have less than or equal to or greater than, right? So basically corresponding to those three concepts, you have big O, big omega, big theta. Okay. I'm not explaining more than that for the purpose of this class, but I explain it with a lot of examples as we go along. Okay. Okay. You can see here Fn is order of Gn if Fn is asymptotically less than or equal to Gn. Remember, that's what it is, right? It's always less than or equal to. It is never greater than. Whereas in big omega, okay, it is not less than, but it is greater than or equal to Gn. You have Fn and Gn, right? So Fn can be less than or greater than or equal to. So less than or equal to is big O. Greater than or equal to Gn is big omega. If it's exactly equal, okay, that is the big theta. Okay. So in simpler terms, that's what it is. Hey, you have some reference function Gn, whereas all the asymptotic analysis that we are doing is eliminating the constant factors. That is the reason why it's called asymptotic, because we are doing an approximation to a reference line. Okay. And then there are three possibilities when you have two functions. It can be Fn can be less than or equal to Gn, or it can be greater than or equal to Gn, or it can be exactly equal to Gn. Corresponding to those three, you have big O, big omega, big theta. Okay. Now again, unless you do some examples, you would not appreciate it, but you have to hang in there. Okay. Uh, F5n squared is, by the way, that big omega, right? Its omega is of the order of n squared there. Um, Different, I mean, again, these things would not make sense to you, so I'll skip them for now. We'll come back to it, don't worry. Okay. There are some values there you can convince yourself. I don't want to rush this particular slide since we are running out of time. We'll cover that again. I'm just introducing them to you. Y Fn squared is is that omega Gn where here you will see that, right? That's the omega Gn where it is greater if Fn is greater than or equal to. Remember that? That is the big omega. Okay. Going back there. Okay, let me stop here if there's anything else. Okay. Now, little o and the little omega. Okay. So, in total, we have five of them. Okay. Big O, big omega, big theta, And then you have two more cousins called little o and little omega. So we'll take a look at extensive list of examples to understand these five things. However, um, please note that most of the algorithms that we do, the focus is really on big O. We don't talk much about big omega and big theta, or small omega, small theta, and so on. They're all interesting concepts, but from a practicality viewpoint, if I understand big O of algorithms, 90% of my ground is covered when it comes to writing efficient algorithms. The question that is posed here, again, I'm not answering any of that right now. You are certainly welcome to take a look at it, because I posted in the slide deck, right? We'll actually be doing some in-class exercises on these things beginning next week. Okay, let me stop here. Questions, comments? I know he said 3 more minutes. I have exceeded my 3 minutes. This concludes uh, today's lecture, and we'll continue with the same concepts, where I'll keep adding to this slide deck. Okay. 175 students signed up. I think there are more than that, right? About 300 to 400. Let's see if we can. Faculty members, please help me in terms of ensuring that all students from your institution have gone uh, and signed up online. So 175 is amazing. I'm impressed. We should beat last class's record of 250. Okay, that's my goal. Okay, Chakravarti garu, I'm done for the day. As always, I can hang on if students have questions. Uh, Chakravarti garu, can you send me the Excel sheet, whatever you have, if you're still there?
Yes, sir.
Without
Yes, sir.
waiting, okay, send me what you have, and then I can correspond with the faculty members. I'll actually correspond with them even before our session. Okay.
So today, by evening, you'll get the list.
Okay, thanks, Andy. I appreciate that. Thank you all, and have a nice day. Okay, I have to sleep now.